Меня зовут Shulzhenko Petr. Мои контакты представлены на экране, который, я надеюсь, виден. Вот, я учусь на ФРТК и параллельно в École Polytechnique. Работаю в R&D над задачами компьютерного зрения. Вот. И I think I should continue in English because this presentation was planned initially in English. So if it's all right for everyone, I guess there shouldn't be a problem. But actually, I should beg your pardon from the beginning because, like, mostly nowadays, my brain operates in French. So sometimes I will experience, I guess, some lack of words, but hopefully it would be all right. Okay, in today's presentation, I would like to talk with you about deep learning-based segmentation architectures. And I will share my humble experience on this topic and share some quite interesting and funny results and experiments. So, as I said, today's outline would be as follows. First of all, we'll define segmentation problem, talk a bit about key metrics, and after that, we'll proceed to the overview of main architecture classes, because actually there are like thousands of architectures of this classical computer vision problem that is widely used in practice. So it's impossible to cover them all, but we'll stop on the most important from my point of view ones. And I will do all this to ensure that we're all on the same page, because like everyone has different backgrounds. Maybe you've had this topic of segmentation during some academic course, but then you've never actually faced it in practice, or you've seen only like mask RCNN model. So maybe it would be interesting for you to look a bit deeper in this topic. And after that, as I said, I will share my experience in some more practical topics like CPU inference. I will give, from my point of view, an interesting idea for annotation acceleration. And then we'll talk mostly about class imbalance, segmentation of thin and small objects, and also like how can we use synthetic data sets to deal with these problems. So let's begin. First of all, how to define segmentation problem. I think everyone is familiar with this task because it's so classical one. But if you don't, I think it's really intuitive from these four pictures. I think I brought this picture from the publication that it introduced panoptic segmentation, but we can actually divide segmentations in three main categories. So first is semantic segmentation, where we can say that we have to make pixel level prediction, so pixel level labeling of all input image. In instance segmentation, we have to first select all the instances and then make their segmentation. And panoptic segmentation is actually a combination of these two tasks. So we have to make pixel-wise predictions, but also we have to distinguish objects, instances in every class. So, as I said, in the input you have image, like during inference, but also like we can say some meta information like number of classes that can be present on this image. And as the output, your model should give the image of the same size with highlighted pixels, so with annotated labeled pixels. Again, I think it should be really clear for the from this practical perspective. So you have in the input an image with an annotation mask. Hopefully, I hope that you will have annotations. So annotations can be mainly in two types. So first, it's mainly used in instance segmentation, is a polygon type. So basically, you would have just images and TXT files for annotations for corresponding images. And in these files, you would have just for every image, for every object on this image, this sort of arrays, we can say. So first element of this array would be class index of this object, and then just points of this polygon area. And the second type is actually annotation masks. So it's just an image with one channel where every pixel value is actually a label of this pixel. And the output of the model, actually, it's not the only way to do this, but I think it's the most logical one. In the end, you have output layer with the number of layers that corresponds to the number of classes. And so during the inference, you just perform argmax operation over all of the channels. Like this, you obtain labels for every pixel. And during training, you can just do pixel-wise cross-entropy loss or every other loss with your ground truth mask, for example. So I hope it's clearer. Now the problem definition. So let's talk about key metrics. We won't stop on pixel accuracies, global pixel accuracies, the stuff like this, because the actual key metrics are intersection over union. I don't think that anyone is surprised. And like its derivatives, like mean intersection over union, frequency weighted intersection over union, etc., etc. And the other key metrics is average precision, because it is still convenient to have one number that summarizes and encodes both the area under precision recurve curve, precision recall curve, and also the form of this curve. But here I just want to highlight that you should pay attention when, for example, you are trying to compare some publications, some models. Yeah, you have to pay attention to the version and the data set on which these measurements were taken, because from version to version, from data set to data set, this metric average precision is named as average precision, but the methods of interpolation can differ. For example, in COCO dataset, we take mean by classes in average precision. In other datasets, we call that mean average precision. Also, we can derive, for example, thresholds for intersection over union. So yeah, this should be taken in consideration, definitely, and yeah, to actually compare the models and their performance. So let's continue with the overview of architectures. Let's start by the Nave approaches. yeah, like we all know that computer vision boomed in 2012. It was. It doesn't matter with AlexNet architecture. Yeah, so not surprisingly, people wanted to adapt these new models to the segmentation task. And first tries were rather naive. That's why I named this slide like this, because actually people just tried to, for example, use linear layers, yeah, dense layers, in the end to produce segmentation masks. So yeah, I think it's clear that there is a huge room for overfitting here. It's extremely computationally inefficient. A bit better approach would be to perform sliding window, take again pre-trained classifier and perform sliding window on the input image. Yeah, and like this, we can classify each rectangle. Yeah, but also it should be clear that like this, sometimes there wouldn't be enough information in this sliding window, and of course it can be efficient. Yeah, this operation. So the great breakthrough was introducing of fully convolutional networks. So we completely removed linear layers in the end, because actually we can think of this type of models as like this, that here we have most weights of the model, and here actually most computations. So yeah, it's pretty natural thing to do in a segmentation task to remove this final actual classifier layers. So people remove that. Now you have dense features here, but in the end, as I said, you have to produce the image of the same size as the input. So people start to do a transformation called upsampling and then transpose convolution. But transpose convolution or deconvolution, actually there is no magic here. It's just upsampling with some convolutional layers. So like this, you can learn a bit more how to correctly perform this operation. Here is a mathematical way of writing it. So yeah, it was a great breakthrough, but there were still lots of problems. Like, for example, obviously upsampling added a lot of noise. Also, here we have dense features, but we lost a lot of spatial information. And actually, it would be important for the future in segmentation tasks. When you, for example, try to analyze the new segmentation architecture, anyway, for me, it's useful to ask me two questions. What is the idea of dealing with spatial information, and what is the idea of dealing with semantic information? Because as we said during the problem statement, in semantic, just in segmentation task, you should localize your pixels and correctly classify your pixels. So yeah, it's always two questions: spatial information and semantic information or context information. So yeah, here we have dense features, but we lost a lot of spatial information, which is actually a good thing for classification, but a bad thing for segmentation. And so like the results were rather bad. So we had to post-process these segmentation masks, which is computationally inefficient. After that, logically, where the architecture of encoder-decoder was introduced. So the convolutional network is basically just this deconvolution or transpose convolution layers that stuck together. Yeah, still the same difficulties like spatial information loss. Dilated convolutions were proposed for this. Dilated convolutions, if somebody speaks French, there is a good name, Atrou. If you speak French, you understand qu'est-ce que c'est. It's just a convolution with a certain step. So like this, you actually you can increase your receptive field. And also there is a problem of scale dependence. Actually, this is tricky question because sometimes people refer to scale dependence as images with different resolutions. And sometimes people refer to this problem as objects with different sizes. But anyways, you should distinguish these two because they're not the same, because like pretty much every model can learn segmenting objects of different sizes if these objects of different sizes were added in the training dataset. So yeah, you should distinguish these two. Yeah, for dealing with this problem, also there were lots of solutions like spatial pyramid pooling or multi-scale dilated convolutions. You basically stacked together several dilated convolutional filters with different steps. Like this, you had like, actually, I think it's kind of analogical with inceptive block. Yeah, inceptive block from classification architectures. And so the major breakthrough was with introducing of UNet architecture. I think most people are familiar with this type of architectures, because here we introduced residual connections in segmentation task. So we have again encoder-decoder architecture with skip connections. Actually, in classificational problem, residual connections is also a pretty tricky question. I invite you to read original papers on batch normalization and residual connections if you haven't read it already. Actually, it's not that simple. What impact introduce residual connections for classification nets, but for segmentation nets, we can think of them like actually we make propagate some space information. As I said, always space and semantic context. We propagate space information to concatenate this rich space masks or feature maps with high encoded features. So this net has an average speed, but also like a huge increase in mean IOU metrics comparing to fully convolutional nets. The next idea was mainstream for the moment. Idea of detect then segment, because it's pretty natural for even our human vision. I don't know if it's biologically correct or not, but I think it's pretty natural to first detect an object and then segment it, kind of this operation. So yeah, it was a mainstream for a while. We used some kind here in famous mask RCNN model, fast RCNN detector or faster RCNN detector. And then after detecting instances, we segmented these objects in corresponding bounding boxes. The major problem with this approach is that we are limited in speed by the speed of faster RCNN, that is actually something like 8 FPS on GPU, which it isn't much, but it's an honest work. What can I say? But the results are pretty good. So you have pretty good metrics. So the logical improvement of this architecture would be using one-stage detector instead of two-stage detector like faster RCNN. So there were lots of types of this kind of architectures, which utilized YOLO detector mainly, or single shot detector, but they were not extremely popular. So for example, here you can see YOLACT architecture. It's a bit trickier than this because yeah, you divide like, you make firstly, in fact, in parallel, you make mask predictions like incorrect masks, and also you predict the actual scores for instances, and then you merge it like this. You have pretty performant architecture with pretty good metrics, because, for example, first version of YOLACT had a speed of 30 frames per second, but the metric was a bit worse than mask RCNN. But the second generation of YOLACT were already comparable with mask RCNN, but extremely more performant. The next extremely interesting class for me, which is also based on detectors, is Multinet class, because it's actually widely used in practice. Maybe it's incorrect to say widely used, but actually there is always a big demand for this kind of net, because it can perform several tasks using one encoder. Like in practice, often you need to classify your image, for example, and segment objects on them, on this image. So yeah, here comes Multinet, pretty handy. Often they use some lightweight encoders. Like this, they can perform in real time or close to this. So let's continue with some modern approaches. So let's start with SOLA. So these approaches would not be based on detectors and on detection. So here, SOLA architecture, I think it's like segment objects on localization, okay, something like this. It doesn't matter, but it doesn't use an object detector, but it uses a principle of center segmentation or center detection, center representation of an object, because you divide your input image in a grid. After that, if an object is in the center of this grid, in the center of the cell, yeah, you perform, after fully convolutional network, in parallel two tasks. Like you predict a category for this cell, and also you predict the mask. And after that, you merge, and you have your final segmentation mask. Like this, you have really great speed and good performance. So we can compare. It's greater performance than masker CNN, and yeah, it outperforms detection-based methods. Another approach, interesting approach. Yeah.
Is it possible to ask a question at this moment?
Sorry, I haven't heard it.
Can you hear me well right now?
Yeah.
I wanted to ask, is it possible to ask a question at this moment?
I think so, but maybe it would be a bit better to ask questions in the end. I don't know, actually, because yeah, like this, this presentation can be a bit long. I don't know. Yeah, I think it's better to ask questions. Yeah, just
no problem.
Keep it in your head. Yeah. So yeah, the next interesting approach was introduced in the architecture of Spar. So you can see that it introduced a new and rather interesting representation of an object. It represents an object as a sparse activation map. So we don't represent an object by its center, for example, like in solar architecture, because, like, for example, the object cannot be in this cell, etc., etc. So cannot be in the center of the cell. So yeah, there can be some problems with this. Also, like regional-based approaches, like detection-based. Here, there could be more than one object in this region. So there are also some details. And because of this approach of sparse activation maps is beneficial. So you can see they use just some first fully convolutional net to extract features on different layers. After that, they perform encoding. Like this is kind of feature pyramid pooling, but a bit faster. After that, you have decoder that predicts masks, and for instances, you predict these activation maps. What is really interesting, you don't need annotations for these activation maps because it can be performed in semi-supervised way. So like this, you can reach amazing speeds with a good metric. So that's a piece of cake, what we need. After that, we can continue with a bit, again, more modern approaches that deal with high resolution images, because actually always before that, we had a trade-off between resolution of an image, yeah, and the speed of our model, because logically, like the greater resolution, the more operations, the slower our model is. But we lose lots of details, yeah, when we resize our images. So this architecture, bilateral segmentation net, proposed a bit different approach to deal actually with this classical thing, how to deal with semantic information and how to deal with spatial information. So they divided into paths. Like here you have just convolutional layers, basically, that extract some spatial information. Like here you have 8th part of the image of the input image resolution. So you divide it by the factor of 8. Yeah, your feature map, and here you're trying to extract some contextual information, about details, etc. After that, you perform attention refinement module, but here actually attention is this one-to-one convolution. So it's attention from channels. We're trying to learn some patterns in the channels, and after that you perform this fusion of these two paths, because of course, like they are from different levels. Therefore, you can't just merge them. So you have to do something like this. And in the end, you have extremely performant, extremely rapid model that actually shows pretty good results on cityscapes dataset that is pretty challenging datasets because the resolutions are high, etc., etc. And then we move on to the models that use attention or self-attention mechanism or even transformers. So I've picked this dual attention network because there are lots of, I personally think, interesting ideas in it. So actually it uses, first of all, kind of ResNet model, but it's not actually, it's a pre-trained ResNet model, but with dilated convolutions, and I think they also removed some poolings or something like this. So you don't have, so it's a bit different. And after that, you have two attention models. First, that actually looks for position context, a bit like global context, and the second looks for patterns in channels, because actually we can view channels as each channel can be viewed as a response, of a certain class, certain semantic class. So like this, we can actually find some interdependencies between them, and use them for better representation of different combinations of semantic classes. And after that, you also perform some sort of fusion of these two paths, like classical thing to do. And you can see that it outperforms BiasNet model actually pretty much significantly, but it's not that rapid. So after that, there are lots of visual transformer based architectures. We can actually spend, like, I think, several days on overviewing this architecture. So it wasn't my purpose. I just wanted to highlight something that, for example, there are several architectures which are time efficient. So you can see that it's rather rapid. Also, like segmentation segformer is pretty efficient, and obviously these modern state-of-the-art architectures, they have the best metrics on most data sets, like CocoStat and Cityscapes and other rather demanding data sets. So that's it for the overview. I hope that you will ask your questions in the end of the presentation. Now I would like to speak more about some more practical aspects which are related to segmentation task from my experience. And my experience is based in segmentation is based mostly on two projects. First project was was done in MIPT laboratory Star Kit that deals with robotics. So it's humanoid soccer league. So in that project, we were trying to find a deep learning segmentation architecture that would be sufficiently rapid, because in a robot we have only a CPU chip, so no GPU. So we're actually rather extremely computationally limited. Like as I wrote, we're limited in RAM, we're limited everywhere, and we have real-time speed requirement because we're trying to play football, so you have to process information rapidly. And the second project in which I'm currently involved is a R&D project in one industrial company. We're trying to automate a production line. For this, we have to perform some segmentation, classification, and detection. So there are lots of details, and we will talk about them a bit later when it will be necessary. So let's talk about CPU inference. Why actually we need it? Because we have GPU cards where it runs extremely efficiently, but in practice, often we have to have an inference of our model on the CPU only chip. Like sometimes, like as I said in the first project, it is just a requirement and constraint of the task, because you can't put a GPU card in the head of the robot, because it's just it's impossible. And in my current project, the problem is just a budget, because the company has already invested money in CPU servers. So this amount of money is rather significant for the company, and also like there are additional costs. The GPU cards are rather expensive. Also, you have to think about hiring people that would actually manage all this stuff. So actually there are lots great motivation to have your model running on CPU. Now let's talk how to do it. Like first of all, you should wisely choose your architecture. Here, from my experience, I would propose you some multinet or object detection based models, which are based on some light one-stage detectors, or we can try to find some modern approach with fast modern approach. After that, you should also wisely choose your model in this architecture zoo. Because of course there are plenty of variants of each architecture, but here you should deal with this trade-off between size and quality that you need. And actually, if you are running on CPU, most of the time you would choose just the smallest versions of the model. After that, to deploy a model, you have to reformat and optimize your model from, for example, PyTorch or TensorFlow frameworks. And this actually depends, highly depends on your target's hardware, because, for example, some optimizations of ARM processors or Intel processors, etc., they're different. So you have to actually take it into the consideration. And after that, optimizations they can be mostly divided by into categories. like optimizations that are performed during the training and post-training. During the training, they produce more accurate models, but it's harder to do this. It takes more time, takes more computational resources. So yeah, it's mostly you try to do post-training optimization if it's not sufficient. It's if the accuracy of the model is not sufficient. But yeah, after that you don't have much choice. You have to perform, for example, quantization-aware training. So here I have tried to summarize framework, what can be done for Intel inference from my experience. So basically, mostly used libraries are ONX and OpenVINA. OpenVINA that is designed for Intel hardware, but sometimes it's a bit challenging. Yeah, for example, theoretically, you can transform your PyTorch model directly to OpenVINA, but from my experience, it's much better to firstly reformat your PyTorch model to ONX format, and then from ONX to OpenVINA, because like dependency problems and other stuff is rather annoying. So after that, you perform all types of optimizations, like operation fusion, quantization, your model pruning, etc., etc. For this, you will have to have representative data set, because most of these operations, they need to have some representative data set to measure some activations, scales of activations, weights, etc., to perform these quantizations and optimizations. And after that, you just deploy to runtime formats. Like this, you have the best performance possible. If the accuracy of the final model is not sufficient, you should try maybe NNCF library, which is actually accessible from OpenVINA library, but also it's accessible like independent thing. Because of this library, you can. It's not easy, but you can perform optimization aware, yeah, during training. Yeah, like this. Most of the times you will, in the end, have better model. So let's discuss a bit more in details. What is pruning? What is quantization, etc. So pruning is much like as pruning decision trees. So you have to have criteria, and then you have like what you cut, and then you have to decide actually you prune connections, you prune channels, or you prune even layers. So you can see here like it's a pruning while training. But in practice, you rather would just select, for example, for pruning connections, you will just select weights with the lowest absolute value. And like this, you will just mask them. Yeah, so pruning connections will improve the size of your model, but actually it wouldn't improve the speed of your model. But if you prune entire layers or channels, yeah, of course, the number of operations will decrease. So like this, you can improve your performance. Quantization is also extremely widely used trick. So in practice, again, most of the times it's simply converting your weights accuracy, from floating point 32 to your target hardware precision. Like most of the times it's int 8, or even less. But there are lots of ways to do it in a much more clever way, like to do it during training with the sharing of the weights. Actually, people perform even k-means to make clusters, to then just have tables of indexes, and like this, you save a bit of computations, a bit of size of your model. And here I should mention that details matter, because changing the way the quantization range is calculated, or do you use asymmetric activation or not? Actually, this kind of stuff, they can they don't impact the speed of your model, but they can decrease the accuracy of your final model pretty significantly. Also, there are rather theoretical things like Huffman coding of your weights indexes, because the distributions are biased, but they're rather more theoretical things or performed by default. The alternative approach to this kind of model optimizations would be a combination of deep learning model and classical computer vision model. I think we would settle with this solution in my current project. So basically, the idea is extremely simple. You have your deep learning model, which can't run in real time, but you make this, we can say, rather precise predictions. You obtain rather precise segmentation maps, and after that you follow it with some sort of the tracking algorithm that track your segmented detected objects. And like this, you can still have your system run in real time, but not your deep learning model. And just to give you some scale, some examples. The most performant model on CPU that I've achieved was YOLO V8 Nano. I've achieved speed of 11 FPS, but my colleague, for example, Semyon Panov, I think he has achieved even higher performance, like from 12 to 15 FPS. So you can see that actually it's possible to have something from 5 to 15 FPS on CPU only device. Let's move on to annotation acceleration idea. So in my current project, there is a problem with annotations, because one class of objects is pretty tiny. It should be precisely annotated, and there are lots of them on every image. So we had to imagine a way to make annotations for this class. So we were not satisfied with CVAT classical options for annotations. So we had to imagine something. So I brought up this idea of interactive segmentation. Actually, it's a really interesting idea. You can see here, during training, for example, for this net, the user has to put a ground truth label on every object that will be annotated. Like this, the model takes it into account. For this model during training, it takes into account like ground truth label. Also, there are lots of ways how you can provide time efficiently these ground truth annotations. But these ways, yeah, they save you a lot of time, but in the end, the annotations are not really precise. So we moved to extreme points annotations. So you can see here, basically the thing is during even inference, you have to provide 4 extreme points of your object. And like this, actually is pretty cool stuff. They add the 4th channel to the image with, for example, Gaussian distributions of each point. And yeah, like this, the model can actually have pretty cool results in the end. Also, there are variants of this model which better perform on thin and small objects, but we were satisfied with this Dexter model. So from our experience, it's something around 10 times faster than just make your annotations in CVAT by polygons. And it's even faster. I'm not entirely sure that by the factor of 2, because I didn't actually make a scientifically proven test, etc. But yeah, it's something like 2000 faster than segmentation anything model, which is kind of hyping right now. And actually it correlates with the measurements that were taken actually in these public publications. So yeah, it can be interesting to use this idea. Let's go on. Let's talk about class imbalance. You can see here an example of segmentation mask in the project of StarKid. Yeah, so it's a humanoid robotic football league. You can see that the class of the lines of the football pitch is rather small in comparison of the whole image resolution. Yeah, basically in practice, often you have to deal with thin and small objects. Yeah, so it's kind of also a class imbalance. For this, you have to adapt your loss function, because standard loss function is pixel-wise cross-entropy loss, but it works well only with more or less uniform class distribution, which is not the case here, because actually, yeah, it's pretty obvious that it treats every pixel independently. Therefore, it can't actually make the difference between the pixel that is misclassified near your small object or just in the other part of your picture, and yeah, all the types of problems like this. So you can introduce some weighted cross entropy, like distance weighted cross entropy, or I don't know, frequency weighted cross entropy. Actually, it works not that bad, but it could be done better. Like you can use dice coefficient. Yeah, so it's something like IU. Yeah, and as it considers only foreground objects, it can be dominated by background. Therefore, it doesn't have the same type of problem as pixel-wise cross entropy. So it's the variance of this dice loss, like generalized dice loss, is widely used in practice. Also, there are lots of generalization of dice coefficients in which you can more penalize, for example, false negatives or false positives, etc., etc. A bit more interesting losses are like, for example, focal loss. Here you introduce this term, to your cross entropy loss that actually changes the weight of well classified examples. So, for example, if you are familiar with online hard example mining, also it's pretty interesting idea. So here you just remove all well classified examples, but in focal loss it's a bit more flexible because you don't completely remove easy examples, but you just assign a smaller weight to them. Another loss would be morphological loss. So actually it's just a combination of cross entropy and cross entropy for small objects, and cross entropy for small objects is just cross entropy after white top hat transformation. It's just a morphological transformation that actually it's like written here, input image minus its opening by some structuring element with a height parameter of its kernel k. So like this, you can assign more, you can focus your network more on small objects. Also, there are like boundary losses, which deal also with unbalanced segmentation. The most interesting one is active boundary loss. So actually it's pretty hard mathematics in it because it uses some graphical network ideas, etc. But no, it was boundary loss for highly unbalanced segmentation. Here you just have also the combination of free losses, because like you have to be able to segment these pin objects to actually have a boundary loss on these objects, because if not, like it doesn't make sense. So it's only a third term, and in this third term you also use weighted cross entropy. So the weights are actually the distances between predicted boundary and ground truth boundary, and cross entropy is actually cross entropy of pullback distances of also predicted and ground truth boundaries. So actually the main idea can be summarized as at each iteration, you are trying to predict the vector of directional vector from predicted boundary to the closest ground truth pixel of the ground truth boundary. And like this, at each iteration, you try to move your predicted boundary to the ground truth. So here are some experimental results that I've achieved. So you can see, for example, in my tasks, focal loss ended with some loss in performance, and morphological loss and active boundary loss. Yeah, they actually improved a bit final metric, but not significantly. Also, they didn't change significantly the stat of bad classified, bad performed samples. So yeah, it's even here you can see it's a graph from the paper that introduced morphological cross entropy loss. You can see that this change of losses can give you a huge improvement of results. But it can give you a slight improvement to, I don't know, like 1%, 2%. Maybe it will give you also change of your learning curve. Yeah, so maybe it would be more responsive to new data. Yeah, so actually I've seen it with morphological loss. But yeah, it wouldn't actually remove all your problems. So for this, maybe you should deal with bad annotations, because actually bad performance samples highly likely was caused by bad annotations. So first option is to enhance annotations, but here we will have to deal with the same type of problems as several slides above. Yeah, or you can use simulation and synthetic data. So we'll talk about it a bit more now. So in StarKit case, because it's robotic football, in which algorithms are trained in simulation environment. So you have actually free annotations from here. Also, you can change like lighting conditions, etc., etc. So yeah, it's a logical thing to use. By adding 40% of the size of the training data set of simulation data, I've improved by 2% my IU metric of this lines class, and also by 5% mean average precision metric for object detection task. So yeah, it's really performant. And in production line case, I've used a different and, as for me, extremely cool solution, because surprisingly it works. So first of all, about the challenges of this case. So there are lots of thin and small objects. We have to have high precision, especially on the boundaries, because if no, it can be practically used. Because of these two factors, it's extremely expensive to annotate, have high quality annotations for them. And also because it's a production line, so you have, hopefully the production line is stable, so you don't have much variance in your data. So you can have several days of videos, but there wouldn't be much change between the frames. So I tested mainly two kinds of approaches. So the first approach was simplify domain adaptation. So I've tried to pre-train my networks on some parts of the data set that would better correspond to the final goal, to the final task. So the data set that incorporates some thin and small objects. I've tried also cityscapes data set with segmentation of the signs. So yeah, stuff like this. But it actually didn't improve significantly the final results after fine-tuning. So I switched to the second approach. Second approach is to create synthetic data set. Synthetic data for this task. Actually, I've done it okay, like thin object 5K dataset. Basically, you just take dataset of background images. You extract your target objects, and you just copy and paste in random positions with random sizes, etc., etc., on these backgrounds. So like this, you have free annotations because you have pasted this object, so you know its mask. Also great flexibility, compared to mosaic augmentation, where you can't actually every time understand what's going on. Here you can manually change some proportions, etc., depending on the task. And also it's like object aware, because you copy and paste this object, and like this you can have a great data variety. Because you, as I said, I've created 4,000 images like this. The biggest surprise that it works. So I've done 3 variations of this data set, because actually it's not obvious that the model in the end will learn something useful, because the model can learn just some, for example, noise distributions, or which are different between background image and foreground object. It can learn just some difference, some boundaries, some difference in contrast, some contours, etc. So it's not obvious that it would work, but it works. And more surprisingly, it works with any kind of backgrounds. So I've tried color backgrounds, I've tried grayscale backgrounds, because in the final task we have grayscale dataset, because the cameras that can deal with high temperatures in our factories, they produce, they give you grayscale videos. And also I've tried to do this kind of dataset with the backgrounds that I've extracted from real dataset, but this actually didn't work well, because I think there were no sufficient variety or something like this, because it was a bit harder to create. So as a result, we have pretty significant improvement of all metrics. Like for classification task, it outperforms by 4%. After fine-tuning on real data, it outperforms all other models that I've done so far, with all kinds of augmentations like rotations, affine transformations, etc. For segmentation task, it also improved mean IU by 4%, and actually it also improved the border blur. So yeah, it's actually kind of significant improvement. And as I said, the data set that I've done with real images, the results were pretty much comparable with the results of the model with standard augmentations. So yeah, I can encourage you to try to give it a shot. Yeah, because it takes like 1 day to do. Yeah, after that, several days to test. But in the result, you can significantly improve your metrics. So that's pretty much all that I wanted to tell you in this presentation. So thanks for your attention. I wish you high quality segmentation maps. Yeah, thanks for your attention. I would be really pleased to answer your questions.
Sorry, just a simple question. In that StarKit project, it's a limitation order. So it's rules of the competition that you could not put the GPU into the robot. Because now we had all that stuff like NVIDIA Jetson, which is a small one, right?
Yeah. Actually, yeah, you can, for example, use. No, it's not. It's not a rule that you can't. Yeah, it's just that you're limited in space. Yeah, you're limited in cost. Yeah, you can use some, even for example, Intel chips. Yeah, for graphical operations. So yeah, it's possible. It's possible. Just in our robots, we have only Intel i7 chip. That's all.
Yeah, because that stuff like NVIDIA Jetson, it costs, well, the nano version, it costs like $100. Yeah, and it's relatively small. So, and it consumes like 10 or 20 watts or whatever at most. So.
Yeah. Actually, as I said, it's interesting. Yeah, it can be done. I think maybe it should be done actually, but yeah.
Mm-hmm.
Regarding to the page number 15,
Yep.
I'm not sure, maybe 14. Well, I'm not sure if you were talking about this fact or not, but what just came to my mind was if we want to detect some object in our picture, then one good way is to firstly use object detection, then use segmentation for increasing speed. Or did you say something like this?
Yeah, it's actually the idea of object detection based architectures. Yeah, firstly you try to detect your object, yeah, with a bounding box, and then perform segmentation actually in this bounding box. Yeah.
So we call it object detection based, which means it's actually segmentation, right? Both segmentation and detection, but the final result is a segmentation, right?
Yeah, final result is the input image. Yeah, where
instant segmentation. Okay, all right.
Yeah. It's
one more question is that this object detection. If you have an model trained for detection and a model that trained for segmentation on the same probably data set, if we is it possible to combine these two for segmentation and detection and get the same result as object detection based? Will they give us the same almost same result with the same speed and quality?
I think that you are trying to actually create this kind of architectures. Actually, you can, and even more, it will outperform these two standalone models, both in speed, because here you use only one encoder, and also there is a kind of interesting theory that it outperforms it even in accuracy, even in precision, because in this type of problem statement, you have more response, because you're trying to perform several tasks, and from each image, the model retrieves more information. You see the point? Yeah.
Yes. Would you mind to go to next slide?
Yeah.
Sorry. The other one, which was explaining about the architecture, maybe it was slide 13 or 16. I'm not sure. Yeah, this. Yeah.
This. Okay.
Well, my question again is that if you want to perform that, firstly, which one would be better? If he detects the object first and then do the segmentation, or do the segmentation then the detection? In my idea, I guess, firstly detection, because it's much faster than when we detect. We only just do the segmentation in the cropped or in the BB box.
You are right. It's just like this. You have firstly your detector, and then you just add a head of segmentation, like So, for example, here is just like here. You have really your fast RCNN, and then you just add several convolution layers to perform instant segmentation. So yeah, it's like that.
Do we have time for another question, or I'm done?
But feel free.
Let's imagine we want to train a model on a task which there is no data set for it. We want to predict something which we don't have any data for it. How can we perform this training? I guess your answer would be synthetic data set, but the thing is that how can we increase the accuracy for the synthetic and the real life if that thing is going to happen? For example, if that event is going to happen, then we don't have pre-trained or data set to check if our model is going to work. Like what, for example, I can make a quick example for you. If someone's going to moon, they don't expect what they're going to see, but they need to, let's say, train something to be accurate enough. How can we do that?
Okay, I think there are two parts of your question. The first, I will advise you to Google few shot segmentation or zero shot segmentation. So it's basically what you are trying to say. It's when you have several examples of your target class or no examples, and you try to perform segmentation, on that. Actually, for zero segmentation task, like segment anything model, for few segmentation task, there are actually lots of interesting idea how to deal with this. As you said, there is a possible solution of synthetic data, but it can be much further. Like people use generative models to generate this. People use two-path models. So
sorry, what models?
With two paths. I will describe it right now. It's a bit hard, without like with just your hands. But actually, you have the first model that actually performs the final segmentation, and the second one, which that is trying to add some relevant information about that. So something like this. If you are trying to segment like a new type of car, and you have you can train your second model on different types of car, and like that, you can create an architecture that will guide this first model to obtain better results. But as I said, there are lots of classes of solutions.
By the fact that you said, is it the same as fine tuning, or they're totally different?
It's not exactly fine tuning. Like it's fine tuning if we take it literally. Like if if it's just the sense of this word in English, yeah, it's fine tuning because you're trying to tune, yeah, you're trying to guide.
I mean, by the
your
algorithm.
model, yeah. Yeah, it's not like fine tuning for me. It's the sort of transfer learning. No, it's not.
Yeah.
It's not definitely transfer learning in its classical format. Yeah.
And the name of it was Two Paths Model?
No, it was the name that I gave it. Really, I just invite you to Google few-shot segmentation overview or something like this. Yeah, you will discover lots of interesting ideas there.
Thank you very much. I appreciate it.
Thanks for you. I think that's all for today then.
Можно вопрос задать?
Yeah. Безусловно.
Пробовал ли ты и помогали ли тебе self-supervised претрение, например, задачи сегментации, когда было мало разметки? Например, предсказывать маскированные патчи на картинке. Кажется, это очень похожая задачка на задачу сегментации. Возможно, претрен может...
Да. Maybe I should continue in English, but I don't know. Yeah, actually, I've had some experience with masked autoencoders. Yeah, and using it both for low supervised or weakly supervised classification and for weakly supervised segmentation. Yeah, it's a bit trickier for segmentation. Yeah, and I would say that in my practical examples, it's much easier to annotate your data set or to create some synthetic data set, etc., than to do this kind of stuff. But yeah, it works. You extract. It's totally possible to extract useful information from this, both for classification and segmentation. And actually, it's how it's performed. Yeah, and in recent publications. But it's you have just to invest some time in that. But yeah, it's actually masking gives sufficiently hard task, for the model to train and to extract useful information.
Thank you for your answer.
But I hope that I've answered. Maybe you can detail a bit and yeah. So I guess it's all right. Thanks a lot for everyone. Have a nice day, week, and the year. I guess so.
And how can we get these slides or the presentation?
It will be published, I think, on the GitHub of this channel. Yeah, so
thank you.
There wouldn't be no problem.
I appreciate it. Have a nice day.
Yeah.
Bye.
Yeah, good luck. Good luck for you all.